Let's say you and your friend are sending messages to each other in binary. And just to make things a little simpler, let's say you only use these characters and space. Now, how do you encode a message in binary? So let's say you want to send the message bad. How would you convert that into binary? Well, one way you could do it is try to come up with a binary representation for each letter, and then you could just put them all next to each other. So there are 8 characters in total here. So we could use 3 bits per character. We could just go like this: 0, 0, 0, 0, 0, 1. Now if I wanted to write bad in binary, I would just go, well, B is 0, 0, 1. A is 0, 0, 0. And then D is 0, 1, 0, 1, 1. Okay. Now, what if my friend sent me a message and I want to decode it? So what if they sent me 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0? How would I decode that back into letters? Well, everything is in threes, so I could just group it up by threes. Now, what's 1, 0, 1? That's F. What's 0, 0, 0? That's A. What's 0, 1, 0? That's C. And what is 1, 0, 0? That's E. Okay, so they sent me face. Now, that's nice, but what if you wanted to be a little more efficient? Let's say you and your friend analyzed your messages and you measured the frequency of every character. So you say, oh, we use E a lot, we use A a lot, we don't really use B and C too much, and so on. So these are the percentage frequencies of how often you use each character in your messages. Now, we can actually take advantage of this by, instead of having everything be an even 3 bits, we could actually say, okay, if something is a more commonly used letter, let's use like maybe 1 or 2 bits, and then we could use more bits for the less occurred characters. That way, the average number of bits per message, given this expected frequency distribution, might be lower. And that would mean you would have to use less bits per message, which could make things more efficient. Okay, so without thinking too much, let's just do this kind of naively. Now we could say, okay, E is very common. Let's make that 0, only 1 bit. A, pretty common. Let's make that 1. The next most common is D. We ran out of 1-bit characters, so now let's try to do 0, 1. Or no, let's try 0, 0. Now, here's a problem. What if I have the message 0, 0? They send me 0, 0. Did they send me just the letter D, or did they send me 2 E's? I don't know. It's easy to encode this a message. So if I wanted to send my friend the letter D, I would send 0, 0. But that means it's easy to encode, but it's impossible to decode because it's ambiguous. Now that's a problem. Okay, what if we change this to something else? Let's try 1, 0 instead. Oh, then we got another problem. If I get 1, 0, I don't know if they sent me AE or just D. So it's a problem. When exactly will this problem occur? If you think about it, this problem is going to happen when one letter's encoding is the exact same as the beginning of another encoding. So let's say these were even longer. Let's say I made this 1, 0, 1, and I made this 0, 1, 0, and then I made this one 1, 0, 1, 0. Now, if I have a message 1, 0, 1, 0, 1, 1, 1, blah, 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 I don't know if this message starts with the letter A or if it starts with the letter D. Because it could start with the letter A, and then this could be the beginning of some other letter, or it could start with the letter D, and then this could be the beginning of some other letter. I don't know. So this problem occurs when one of the letters encodings is a prefix of another letter's encoding. So we have two problems here. How do we create an encoding that doesn't have this prefix problem so we can actually decode it and it could be useful to send messages between you and your friends? And also, how do we generate the most efficient coding such that the average expected number of bits per message given this distribution is going to be minimized? And there's actually one pretty simple way to do all of this at once. So we start out by taking the two least common things, and I'm not going to say letters because soon there are going to be letters and something else. So let's say we take B and C because they're 5 and 5. All right, we have B and C, and I'm going to make these nodes up here. So we have 5 and 5, and now I'm going to take the total for 10 and connect them to these B and C nodes like a binary tree. Okay, now we have 10 and then the rest of these. So B and C are out, and what we do next is we take the next two lowest frequency things, and we consider this node to be a thing. So we have 10s are the lowest. So let's just go from here and do F and G. Actually, I'm going to give a little bit more space. So we have F and G, we have 10 and 10, and this goes up to 20. Okay. So F and G are done. Now we have another 10 and this 10, so let's do that. So this is going to be space, which has a frequency of 10, and then we connect these two up. The total is 20, 10 plus 10. All right. Now we have 20, 20. Oh, we got a 15 over here. So we were done with that. So the lowest things are 15 and either that 20 or one of these 20s. Let's do the A20. So we'll do another tree over here. We'll do the AD for 20 and 15, which has a total of 35. All right. Now we have a 25, a 35, a 20, and a 20. These are the two lowest frequency things. So we're going to connect these. Makes a nice 40. All right. And now we have a 40, a 35, and a 25. These are the two lowest, so we're going to take this E, which is a 25. All right. This is a total of 60. Now, there's no letters left, so our only choice is these two nodes right here. So we're going to get a total of 100. All right, now we have this nice binary tree. And it's structured such that the least common things are the furthest away from the root. Okay. So, but how does this help us come up with an encoding? Well, here's how. If we say going to the left is 0, going to the right is 1, and we fill that in for all of them. Now we have an encoding from this tree. So E is going to be 0, 0. A is going to be 0, 1, 0. D is going to be 0, 1, 1. F is going to be 1, 0, 0. G is going to be 1, 0, 1. Space is going to be 1, 1, 0. B is going to be 1, 1, 1, 0. And C is going to be 1, 1, 1, 1. All right. But does this have the prefix problem? Is this a decodable encoding? Yes. And the way you could actually intuitively tell is, how would it even be possible for one of these letters to be a prefix of another? Since this thing is a tree and all the letters occur at the leaves of the tree, the only time one bit string is a prefix of another is if they're part of the same path in the tree. So 0, 1 is a prefix of 0, 1, 0. But since the A occurs at the leaf and there are no children nodes of a leaf, it is never going to be the case that one letter's encoding is a prefix of another, because that would mean that one letter has to be a child of another letter, which will never happen based on how we made this tree. Pretty cool. And it also happens to be the most efficient way because of how we use the frequency to construct the tree, and how the lowest frequency things are the furthest away from the root, which means their path is the longest, which means their encoding has the most bits. That's an intuitive reason as to why this is the most efficient, but it's not a rigorous mathematical proof. I think it's pretty cool that just making this tree like this with this simple algorithm of just taking the lowest frequency 2 nodes and then pairing them together like this constructs the most efficient encoding without the prefix problem. I think that's really cool, and it's just so amazing how just the structure of the tree guarantees the prefix problem, and the fact that we use these lowest frequency nodes guarantees that it's going to be the most efficient encoding. All right, let's actually code this thing. So first I'm gonna paste in some sample text. In reality, you would just use whatever messages you sent to your friend if you're doing that, or any text that you think is representative of the distribution of characters in your communication. So first we're going to make the classes for our binary tree. So we need a node class, which has a left node, a right child node, and its frequency. Alright. Then we have a leaf class, which has a character and a frequency. So this is going to represent just the character at the bottom, like how we start. And the node class is going to represent a combination of either 2 characters or 2 other nodes. Okay. Now, the first thing that we need to do is make the initial forest, which we're actually just going to start out as just doing every letter as a leaf. So it's going to take in the text. First thing it's going to do is make the text lowercase, just so we don't have to deal with uppercase versus lowercase to make the encoding more compact. Now, we want to create a dictionary of frequencies, and this is going to map our characters to their frequency of occurrence in the text. Now, we want to make sure that even if we have never seen a character in our sample text, we can still encode it. We would just treat it as a frequency of 0. So here's just all the legal characters that you might type. And if those aren't in the source text, they're going to have an encoding, or they're going to have a frequency of 0. Now we loop through all the legal characters. and we set the frequency to 0. Next, we loop through all the characters in the text and we count their frequencies. Now, this step isn't really necessary since we're doing this, but let's say you use a character like a slash that isn't in here but is in the source text. Might as well have this line there just to account for that. Next, we're actually going to initialize our forest as an empty list. And for every character in the frequencies, we are going to create a leaf node. So we're going to get the frequency is the frequencies character. And then we are going to append to the forest a new leaf node, which has the character and that character's frequency. And then once that's all done, we could just return it. Now let's just make a forest. So we'll call the initial forest, make initial forest from sample text. And then let's just print it out to see what the frequencies look like right now. So we're going to print them out in sorted order so we could see all the encodings. So as we can see, if we look at the text, looks like only the number 3 shows up. So, or maybe some other ones do too. Is there a 1? Oh, there's an 8. Oh, whatever. So most of the numbers have 0 occurrences. The most common character is a space, and then after that is E, which is the most common vowel. And then we could see that less common characters have lower frequencies. Okay, so pretty cool. Now we have all of our frequencies. Next thing we need to do is combine our forest, which right now is just all the characters and their frequencies, which is kind of like how we started when we were doing the algorithm by hand. And we need to combine that into one big binary tree. So let's make a function for this. And we are going to keep going while the length of the forest is greater than 1. And the reason that we're going to do it like this is because we're going to keep combining nodes and leaves until there's only one root node. And when that's true, the length of the list of trees, which is what a forest is going to be 1. And then that's when the loop is going to stop, and that's when we're done. So we need to write a function to get the frequency of a node, and you'll see why in a second. And we could actually just say return node.frequency. And the reason that we can do this is because it's called .frequency in the node class and .frequency in the leaf class. Now, it's important to note that this might not be a node, capital N node. It could also be a leaf, but it'll work either way. And now the reason we need this is because we need to get the minimum frequency nodes in our list of trees or our forest. So what we could do is we can get the first minimum and we get the min of the forest, but Python doesn't know how to take the minimum of a list of nodes or leaves, so we have to give it a key equals get frequency. And so this basically converts our node or leaf into a number, which is the frequency. And so we're going to get the minimum by frequency. So that's why we needed to write that function before. Now we could just remove that min1. And then we're going to do the same thing again. Min2 equals min forest key equals get frequency. Forest.remove min2. And then after that, we're going to make a new node. from min1, min2, and the frequency of this new node is going to be min1.frequency plus min2.frequency. And so that's kind of, this is basically when, this is the step when we combine two nodes together and add their frequency. And we are removing these nodes from the forest because now they're part of this new node. But right now the new node's just by itself, we haven't really done anything with it yet, so we're going to add it to the forest. Now, min1 and min2 are out of the forest, combined into this new node, and the new node has replaced both of them in the forest. Okay. Now, this is just going to keep happening over and over again. It's going to get the two minimums, and in the end, the forest will just be one single node, which is going to have the entire binary tree of all the things. And so we could just return forest 0. Okay. Now, here comes the hard part. How do we actually generate this encoding and the decoding from our node root? Well, first thing we want to do is we could just get the root from our initial forest. Okay. Now we need to add some methods to these classes. So let's do decoding first. Now, decode self, and it's going to take in a list of numbers, which are each either 0 or 1, and we'll call that bits. And what this is going to do is it's going to take this list of 0s and 1s and convert it to this decoded message, which I will initialize to just be a blank string. And then we say, while there are still bits left, to decode, we could say next character bits equals self.decode next character bits, and then we will add that next character to the decoded message. And now this method doesn't exist yet. What this is going to do is it's going to go through the tree, go all the way down with the 0 and the 1 going left and right, and it is going to consume bits as it goes. And in the end, it's going to find a character at the leaf, and it's going to return that, and whatever bits are remaining after those have been consumed. But for our purposes right here, we're just going to assume that already exists. And then what this is going to do is it's going to keep consuming bits, getting the next character, adding it on, and when it's all done and there's no bits left, we're just going to return the decoded message. Now let's actually get to writing this method, which is going to do most of the work. So we have to decode the next character, self. This is going to take in just the bits. Now, if there are no bits left, then we need to raise some kind of error. Because we are a node, which means since we're a node, we have to consume bits in order to decode the next character. And if there are no bits left, we cannot consume another character. So this must have been an error. This must not have been a valid encoding. Okay, but now to the real part. The next bit that we need to look at is the first in the list. And the rest of the bits is bits 1, colon, colon. And now what this does in Python is, this is basically, let's say the bits are 0, 1, 1, 0. This is going to give us 1, 1, 0. So it's going to be everything except for the first one. Okay. Now, if the next bit is 0, then what we need to do is return self.decode next character. Oh, not self. Self.left.decode next character of rest bits. Otherwise, return self.right.decode next character. Rest bits. And what this does essentially is, if the current bit is 0, go to the left, consume that bit by returning rest bits. Otherwise, go right and consume that bit using rest bits. And the bit where the bit is being consumed is in this rest bits, where we get rid of the first one and only look at the rest. That's where the bit is consumed. And what's going to happen is, based on the bits, we're going to either go left and right all the time until we hit a leaf, and then when we hit a leaf, we just return the character and the rest of the bits. So now we have to implement these methods in the leaf class. Def decode self bits. And you really shouldn't be trying to decode in the leaf class, so we're just going to raise an error. Because think about what it means to be calling decode on the leaf class. That means the leaf is the root of the whole tree, which means you only had one character in your sample text, which means you really can't do a valid encoding at all. So now we have to write this helper method. And now here's where it gets interesting. We could literally just return self.character and bits. And the reason that we can do that is because, let's say this node was just, if you go to the left, it's A. If you go to the right, it's B. And A is 0, and the encoding for A is 0, and the encoding for B is 1. If we do this, it's going to consume that 0 bit right here. Let's say you want to decode the message 0. What's going to happen is it's going to decode, it's going to say next bit is 0, rest bits is an empty list, and then when we get down here, bits is going to be an empty list, and we say, oh, well, if you got to me, that means you must have consumed the bits to get to me in the binary tree. So I just return my character, and then I'm assuming you already consumed the bits, so we're already done. So that's very nice. That is decoding finished. Now we need to do encoding. Now the way I'm going to do this is by generating a dictionary from character to list of bits. So what we're going to do is we're going to have a method called generate encoding. And we're going to start out by just having this list be empty. And we're going to have a helper method, which is going to take in the path so far of bits, which is going to start out to be nothing, and our current dictionary of encodings, which is going to be a dictionary from characters to list of numbers, but those numbers are only going to be 0, 1. And so what this helper method is going to do is it's essentially going to go down through the tree, keeping track of the path and everything, and it's going to add every character to this encoding dictionary by mutating it. So by the end, when this method is finished calling, it's going to have gone through the whole tree, it's going to have added everything into encoding, and since dictionaries are passed by reference, mutating encoding in another method is going to mutate it here too. So the changes propagate back up to here, so we could just actually return encoding. Okay, now let's write this helper method. Oop. Def generate encoding help. Self, this is going to take in a path and an encoding dictionary. And right now, in this class, all we're going to do is self.left.generate encoding help. And now, on the left side, we're just going to add a 0 to the path and give it the same encoding. And we're also going to do the same thing for the right, except we're going to give the right a 1. Now, what this means is we're going to say, hey, everyone on my left side, whatever the path is right now, I'm going to add a 0 to it because I just went to the left. And on the right side, I'm going to say, okay, I just went to the right side, I'm going to add a 1. And what's going to happen is when you get to a leaf, you're going to have the path of how to get to that leaf in this path list. And then that's just going to be the encoding. So now when we get down here, and by the way, we don't need to return anything here because the job of this method is just to change this encoding dictionary, which is going to happen in the leaf class. We don't actually need to return anything. So let's do that over here. Def encode. So really, or not encode, generate encoding. Now this should never be called because you should never try to generate an encoding just based on a leaf. So I'm just going to throw an error right here. Okay, now let's make that helper method, which is going to do the work. Okay, now this is actually pretty simple. All we do here is, since the node class did all the work in accumulating that path all the way down to us, the leaf, all we have to do is say add myself, my character, to the encoding. And what is the encoding of my character? The path to get to me. That's it. What's going to happen now is all the leaves are going to get reached with whatever path it takes to reach them, and they're going to register themselves in this encoding dictionary based on their path. And that is the encoding. Now, to put it all together, we can do this. So let's make an encoding out of this root node. Generate encoding. Okay. Now remember, this root node contains all of our characters, so it contains enough information to generate the encoding for our whole system. Okay, now let's print out this encoding. Whoop. There we go. So let's run this, see what it looks like. I'm going to print out the encoding with the most common letter first. So the encoding for space is 00, which is good because space occurred very frequently. E also has a pretty short encoding. And as the letters get less and less common, the encoding gets longer and longer, which doesn't really matter because those letters probably aren't going to be used very often anyway. And if you check, there is going to be no prefix problem. You will never see one letter's encoding being the prefix of another letter's encoding. All right, now let's make some functions so we could actually use this thing easily to quickly encode and decode messages. So let's make an encode function that takes in a message and a root node, and let's just make the message lowercase just so we don't have to worry about that. And we're going to generate the encoding. Now we need to, so we're going to initialize this encoded message to nothing. Oh, not nothing, or not an empty string, an empty list, because these are going to be lists of 0 or 1. And then we have to loop through the characters. For each character in the message, if the character is not in the encoding, which means it's not a key of the encoding, which means it doesn't know what character that is, then we have to raise an error. Unknown character. Okay, but otherwise we're all good. All we have to do is take the encoded message and add the character, or add the character's encoding. So this is going to add that list of 0s and 1s to our encoded messages list of 0s and 1s. And by the time we loop through all this, we're just going to have a long list of 0s and 1s, which is all the encodings of each character. And then all we need to do is return it. There we go. Okay. Now, that's a nice function for encoding messages. What about decoding? Well, that's also pretty easy. You take in the message that you want to decode and the root, And all we need to do is return root.decode message. All right. And that's it. That is how you encode and decode based on the source text. Let's play around with this a little bit. So we have our sample text still. And we still have a root node. So let's decode a message, or let's encode a message. Let's encode the message hello using the root node. And here's the encoding. Now let's decode that to see if we get back hello. Oh, forgot to put the root. There we go. Pretty cool. So that is how you generate an encoding for letters that it does not have the prefix problem and is optimized to be as short as possible, assuming a certain distribution of frequencies of letters.